and welcome, class. We're here today. We are going to finish up our discussion of Chapter 4, where so far in this chapter we have discussed electron configurations and how they contribute to atomic properties such as reactivity, size, and metallic character. Today, we are going to wrap everything up by talking about how these electron configurations also determine what the ionic charge of a certain species is most likely going to end up being, and looking at some ionic periodic trends. All right, and then we're going to call it a chapter. Once we know how we can make ions from these electron configurations, this is the perfect launching point to get into Chapter 5, where we are finally going to start building molecules. So let's talk about these ionic charges first, right? We want to make sure that we can walk before we can run. All right, so let's revisit the definition of what it means to be an ion, as well as introduce two more specific terms pertaining to how we describe ions. All right, so an ion, by definition, is an atom with a charge. Notably, the charge arises due to a discrepancy in the number of protons versus electrons that an atom has. So we've talked about this back in Chapter 2, that ions come about from the electronic count in an atom being off compared to the number of protons. Now we have these two additional definitions down here that we are going to discuss and talk about, and these definitions, cation versus anion, are used to describe either atoms that have a positive charge, so these are positive ions, or those that have a negative charge, so these are negative ions. So a cation is an atom that has lost electrons. Because this atom has lost electrons, it's going to have more protons than electrons. It's not going to have a net neutral or zero charge. In fact, because of the excess of protons it has in the nucleus compared to the number of electrons, this is where we're going to get the positive charge. A cation, or an anion is an atom that has gained electrons. So now it has an excess of electrons compared to the number of protons, and this excess of electrons is what gives us the negative charge that is present inside of the atom. Now, a way that we can remember these two terms, like a little mnemonic device that we can use if you haven't heard these terms before, I have a couple for you. The one that was the most useful for me, because I'm so much of a visual person, is that a positive charge is represented right with this little plus sign. And inside of the word cation, we can see a T, which, all depending on how you write it, ends up looking like a little plus sign. So cations have a positive charge. Cations are positive ions, and you can tell because there's a little plus sign right in the name. Now, a second mnemonic that you can use to remember that cations are the species that have the positive ionic charge is that a cation is positive, right? Cats have pos, cations are positive. If you're a little bit more of a fan of puns or plays on words, this might be the mnemonic for you. So if you're more visual, you can go with the first. If you're a little bit more punny, you can go with the second, just so long as you remember that cations have those positive charges, because again, we have this little plus sign inside, and both of these things represent a loss of electrons and a positive charge as a result. All right, so we have some examples of ions down below. We've actually worked through these examples already, observing oxygen, neon, and sodium with their 8, 10, and 11 electron counts. 8, 10, and 11 proton counts, we've just been talking about electrons so much. So they have 8, 10, and 11 protons, respectively, but in each of these hypothetical species in this example, we can see that they all have 10 electrons. Now, we've introduced this term before, isoelectronic, meaning same number of electrons. But today we're actually going to be comparing a number of isoelectronic series, so I wanted to redefine this term. As long as we are looking at a bunch of atoms that all have the same numbers of electrons, we would say that they belong in an isoelectronic series. we can compare them together because we have at least one variable in control, the numbers of electrons. Now in oxygen, where we are looking at 8 protons versus the 10 electrons, because we can see that we have 2 more electrons present, there are 2 more negative charges than what we have positive charges, and this leaves us with a -2 charge overall. Now this -2 charge is what leads us to call oxygen in this -2 form an anion, right? It's got a negative charge. Neon, with its 10 protons versus its 10 electrons, has a 0 charge, which means that our neon is not an ion. It is just a neutral atom. And last but not least, our sodium, with its 11 protons versus 10 electrons, we can see that it has more protons present compared to electrons. This is what gives us a +1 charge overall and allows us to call sodium in this form a cation. All right, so this is what we're going to be working with today. We're going to be comparing some cations and some anions. We're going to be comparing some isoelectronic series and their corresponding trends. Now that we have introduced these definitions, though, let's spend a little bit of time talking about how we know the total numbers of electrons that a certain atom is likely to have in its ionic form. All right, so there are 2 different sets of rules that we have to pay attention to. The first pertains to what we call main block ions. In order to determine the ionic charge of what is known as a main block ion, these are going to be elements in the S and P blocks. These elements are going to gain or lose electrons in order to achieve a noble gas configuration. Now, there's nothing, I would say, observationally or inherently special about the noble gas configuration. What we are going to say, why it is that elements strive for the noble gas configuration, this is just observationally true. It's stable. The noble gases are very inert. They do not react with other things. Noble gases are inert, that INERT, inert, because they are stable. There's something implicitly stabilizing about the electron configuration of a noble gas species. Why? It is because the orbitals are full. We don't have any unpaired electrons. There's nothing overtly reactive about it. Everything is content. Main block elements strive for a complete octet. They want 8 valence electrons, because 8 valence electrons means that their s orbital and all 3 of their p orbitals are completely full. So that's what we're going for here. Whether the atom ends up turning into a cation or it turns into an anion, what we're looking for is the path of least resistance that gets us to 8 valence electrons. Again, because 8 valence electrons signifies that we are working with something with a noble gas configuration that is very, very stable. So for an example, let's look at aluminum versus oxygen. Now we can see that there are a couple of ionic forms already given to us, aluminum 3+ and oxygen 2-. We're going to, by observing the electron configurations of the neutral elements, discuss and really showcase where the +3 and the -2 are coming from. How can we predict these charges? Well, the electron configuration for aluminum, if we observe the periodic table and write it out in noble gas configuration, is a core of neon, a 3s2, and a 3p1. So, again, each of the main block ions that we are looking at here, aluminum, which is a p block element, oxygen, which is also a p block element, these are striving for 8 valence electrons. Now we can see that there are two different ways that we can get from aluminum's natural, like neutral electron configuration to a complete octet. Either we can lose these 3 valence electrons. Since there are only 3 here, we could just lose these and be left with the neon core. Or we can add 5 valence electrons. Since there are currently 1, 2, 3 electrons here, if we add another 5, that gives us the total of 8. So we have 2 options here. We either lose 3 or we add 5. Elements are inherently lazy. Again, we are looking for the path of least resistance. The less amount of work we have to put in, the more likely this is going to be the outcome. So between losing 3 and adding 5, we're going to do the least. We are not going to add 5. That requires adding 2 more electrons than comparing to the total we would have to lose, which is 3. Lose 3 versus add 5. We're going with the lesser work that we have to do. We're going to lose all 3 of these valence electrons in order to make aluminum happy and give it a noble gas configuration. This is where the stable charge that we can see presented here comes from. Aluminum 3+ arises because we lose these 3 valence electrons in the neutral configuration, and it leaves us strictly with the electron configuration now equaling that of the core of neon. This core is going to be very stable. The electrons are not going to be very reactive. The ones that do remain, they're going to be pretty tightly bound to the nucleus, but as a result of the loss here, the core is now very, very stable. All right, so the same approach we can take whether or not we are looking at a cation creation like this aluminum 3+, or an anion creation like this oxygen 2-. Again, let's start by writing out the electron configuration of our oxygen. So oxygen has a core of helium, a 2s2, 2p4 on top of that. So we can see that we have a total of 1, 2 plus 4 equals 6 valence electrons inside of our oxygen. So again, if the goal here, because this is a main block element, it is in the p block, if the goal is to reach a total of 8 valence electrons, we could either lose 6 valence electrons, or we could gain 2 valence electrons, right? Because there are currently 6 electrons here. If we gain 2, that gives us a new total of 8. So just like before, we are going to take the path of least resistance between losing 6, which sounds like an awful lot of work, or gaining 2, because there's only 2 additional electrons we have to add. We're actually going to follow this path of least resistance. We are going to gain 2 electrons and slap that onto our configuration as opposed to losing 6. Now, if we gain 2 electrons, what this gives us is the noble gas configuration equal to neon. So we found another way to reach a noble gas configuration, coincidentally also equaling neon here, and in doing so, by gaining these 2 extra electrons, our oxygen gains a -2 charge. So this is how we can explain for the main block elements what the expected ionic charges are going to be. Are we going to be are we more than likely going to lose electrons like we saw in aluminum? Or are we more than likely going to gain electrons like how we saw with oxygen? All right, so this was the first set of rules, those that pertain to elements in the S and P blocks. So what about the elements in the D and the F blocks? We are going to restrict our conversation to the D block ions. This conversation we're about to have could also extend a little bit into the elements that are found in the F block, those lanthanides and actinides. But by the time we get to the F block series, we're also looking at pretty complicated electron configurations, and our expected charges can vary even a little bit more than expected. So let's just focus on the D block. The elements that are the transition metals. Elements in the D block will lose electrons to either achieve a complete or symmetric subshell. So we're not just looking at completing an octet here. We are looking to achieve symmetry. Either that or a completely full subshell. So what we're going to do is break down the electron configuration of iron and use it to discuss how we end up with a +2 and +3 option for the ionic charges of iron. Now, both of these are not hypothetical. Both of these are pretty readily available just in the world around us. Iron with the 2+ charge commonly comes in substances like FeO, which is pretty stable, just like, and can be found out in the dirt. Iron with a 3+ charge is actually the same form, Fe2O3, as rust. So whether or not we're finding dirt or rust, both of these charges are inherently stable. So let's talk about where they're coming from and how we end up with two different options. So the electron configuration for a transition species like iron, we can draw down below. We start with an electron configuration that is argon with a 4s2, 3d6. All right, so just by looking at these numbers, it's not completely obvious as to where our electrons are that are going to be the most easy to lose. So actually what we're gonna end up doing is taking this electron configuration and redrawing it in terms of our orbital box diagram. When it comes to observing d-block elements, and again, for the most part, f-block elements, looking at the orbital box diagram, which we learned how to draw in chapter 3, is going to give us a really good idea for where the kind of excess electrons are in terms of symmetry. So let's redraw this. We'll stick with our argon noble gas core, so we're not going to change this at all, because again, these are the unreactive electrons. Our 4s shell is going to be here, and there are 2 electrons inside of it. And the 1, 2, 3, 4, 5 3d orbitals are here, and there are a total of 1, 2, 3, 4, 5, 6 electrons inside of it. Okay, so when it comes to picking and choosing which electrons are going to be the most easy to lose first, electrons that are in the most valence shell are going to be the ones that are going to be the easiest to get rid of. The most valence shell is going to be the one that has the highest quantum number associated with it, which in this case is going to be our 4s shell. So the electrons that are going to be lost first are going to be lost from the 4s shell. The first of the electrons that are going to be lost are going to be these 2 right here. So we're just going to get rid of these. Getting rid of the first 2 electrons explains our iron with a 2+ charge. However, we now have 1 pair of electrons present in the 3d subshell, and now vacancies present in the 4s. Since we just lost these 2 electrons, they're completely gone. We're now looking at the electron configuration of our iron 2+, at least at a cursory glance. At least at first, this is what we would assume. What's really cool about electrons, again, is that they're very dynamic. They're in constant motion, and they're going to find the place that is going to give them the least energy, the easiest place to hang out. So what we're actually going to end up seeing is that, yes, we have lost our 2 electrons here in the 4s shell, right? Most valence, we lose them first. This 1 electron that is present is like, a vacancy. I'm going to move out of this apartment I'm living in with my roommate, and I'm going to move into my own place. So what we are going to do is lose or shift this 1 electron from the pair over into the 4s shell. One of our electrons is still present here, so I'm just going to clean this up so we can see explicitly the picture that we are working with. We're going to get rid of that. So we had 1 pair. One of the electrons in the pair saw the vacancy left behind by the 2 electrons that we just lost and shifted on over into this open vacancy. Right, if you're living with a roommate and suddenly the apartment next door opens up, you're just gonna move on over. You have more space for yourself this way. So the electron now that has shifted over in the configuration of the iron, the Fe with a 2+ charge. If we kind of condense this back down now into the electron configuration form, we would rewrite this as argon with a core, 4s1, since we have one electron spread out, nice and even here, 3d5. Left over, each of these electrons now with their own little space. This is what we mean in returning to our definition that we introduced up on top. What we're looking for, elements with d-block or electrons are going to lose electrons and then shift in order to complete or form a complete or symmetric subshell. Here now we have symmetry. Every single orbital has one electron. This is a pattern that they are all meeting, a pattern that they are all compromising to. They're all trying to match. So now that we have this really nice symmetry and this really awesome and unique looking electron configuration, we have our iron with the 2+ charge. How we can explain the iron that is present with a 3+ charge is, well, now we have another 4s electron. Right, the electron that moved out from its pair into its own space is now higher in energy. Because it's higher in energy, just by base definition of how these quantum numbers works, it's actually going to be pretty easy to lose this electron now as well. If we lose that electron because the 4s shell is higher in energy, we've now lost a grand total of 3 electrons, and this is going to correspond, what is left, to the electron configuration of iron with a 3+ charge. In fact, I'll even label this one down here, iron 2+, and this is iron in the neutral form. So we have iron with a 3+ charge, having the electron configuration of an argon core, 3d5, and this is going to be it. No more of these electrons that are left in the 3d subshell are going to have incentive to move over into the 4s subshell, because now this subshell still is nice, it's perfectly half filled, all of the electrons are the exact same in terms of energy and dispersion around the atom. It just makes sense for all of these electrons to stay put. So we have a stable possibility for an iron with a 3+ charge. We have a stable possibility for iron with a 2+ charge, and we have our stable starting point with for our iron that has no charge. So anytime we are working with a transition metal, we have to observe where the electrons are in terms of the orbital box diagram, and this is going to give us an idea for how many electrons we're going to be able to lose and where the electrons are going to be after they've kind of settled back down into their final configuration. All right, so regardless as to how we make our ions, once we have them, the cations and the anions both, we can make some predictions about either their sizes, like we're looking at here, or their relative energies after the electrons have been lost. So let's look at some of these ionic periodic trends. Well, what we have been able to observe is that cations are smaller than their neutral counterparts, their neutral elemental starting points. And anions end up being larger than the corresponding neutral atoms or elements. And I mean, the reason why is pretty straightforward when we think of it. A cation is caused by the loss of electrons. So if we're losing electrons, we're literally losing the thing in an atom that gives it its size. So if we're losing electrons, the resulting ion, of course, is going to be smaller. We're losing size. We're losing a piece of the atom. Anions, which are the negative counterparts, are caused by gaining electrons. And because we have extra electrons, we're going to inflate the size of the ion compared to the neutral atom. So it just makes sense, right? Cations are going to be smaller, anions are going to be larger because we've either lost or gained electrons respectively. Now we can compare the corresponding ionic radii as a result in the isoelectronic series for any given element or ion, and it's like with its stable ionic charge. So what we have illustrated here on the right is a chunk of the periodic table, specifically a chunk of main block elements, ranging from the first 2 columns on the periodic table. You can see here we skipped the transition metals. We're just looking at the third like major column on the periodic table, which is technically either group 3A or 13. So this is going to be where like boron is. We can see aluminum's directly underneath it. 4A/14, 5A15, etc. Inside of this box, with kind of the peachish background, we have labeled or signifies an isoelectronic series. So each of these ionic species inside is going to have the same number of electrons. Whether we're looking at sodium with a +1 charge, meaning that it now has 10 electrons, or magnesium with a 2+ charge, meaning that it has 10 electrons, all the way up to oxygen with a 2- charge, meaning that it has 10 electrons. Each of these species has 10 electrons inside of the peach box. What we are comparing, what these numbers correspond to, in blue, we have the natural or neutral size of the element, and we can see as sodium has lost an electron, it has lost size. So it has a smaller atomic radius now. This is also what is being symbolized with the illustration up on top, where the blue half or semicircle corresponds to the natural element, right, with no ionic charge. And in gray, this is now the ionic radius. So we can see that it's definitely shrunk in size. Now, as we work our way from left to right on this, or in this isoelectronic series, we can see that the natural element size steadily decreases. So the blue numbers on the left compared to the red numbers on the right get smaller and smaller. This is in line with what we've talked about already. As effective nuclear charge increases from left to right, we see a contraction in the atomic size of your, a decrease in the atomic size of your atom. This becomes flipped when we look at the ionic size. So we can see that sodium with a +1 charge starts with a distance or a radius of 102 picometers. By the time we move to magnesium, we can see there's a size of 72 picometers and then a size of 54. Contrast this with the elements that we're looking at that have the negative charges, these anions, where we can see the distances or the radii here are 146, 140, and 133. So what gives here? Like, it doesn't look like we have one really nice trend from left to right or from right to left. As it turns out, the element that has the greatest positive charge, so that would be aluminum 3+, is going to be the smallest. And conversely, the element with the greatest negative charge, which is going to be nitrogen with a 3- charge, is going to be the largest. And all of the other ions kind of fall in line in between. So the species with a 2+ charge, which is magnesium 2+, would be next in terms of size. Sodium with a 1+ charge would be after that. Fluorine with a - charge would be after that. And oxygen with a 2- charge is after that. So we're going from the smallest element that has the most positive charge to the largest element that has the largest negative charge. All right, so this is how we can think of and explain atomic radii and that trend versus ionic radii and that trend. Really, in order to get a good comparison for cation size versus anion size, we have to be working and comparing an isoelectronic series. The reason why is each of these atoms presented has the same number of electrons, so the only thing really that differs is the ionic charge itself. So we're kind of keeping in line with the numbers of electrons and only allowing the respective charges to vary as we observe an isoelectronic series. The next trend we are going to look at is that of ionization energy. So this is the minimum amount of energy, because of course we can always put in some type of excess. So this is the bare minimum amount you need to remove an electron from an atom. And by definition, we're also working in the gas phase here. This is just to ensure separation of atoms. So we're not, we don't have to break any additional bonds. All of the atoms are already separated. Literally the only thing we're doing is taking an electron and scooping it out. The ionization energy and this type of property is a form of chemical property. The fundamental identity of the atom chemically changes as we remove an electron. A really good example for this, like how we can explain this as a chemical property, is if we observe sodium versus sodium plus. Now, sodium, even in its gaseous state, is a neutral alkali metal. This thing is very reactive with water, right? You wouldn't want to put it, you don't want to like add it into any type of like aqueous solution. It could catch on fire, the least of which, let's say, would be your mouth. You don't want to put raw sodium inside of your mouth. It will burn your mouth. The reason why I use that as like a very extreme example is because sodium plus is a component of table salt. You do want to put this in your mouth. I mean, obviously not in excess, it just tastes bad, but like table salt is used to flavor food. This is something that tastes very good to us. The chemical property of how sodium versus sodium plus interacts with water, specifically even the water inside of your mouth as a really personal example, fundamentally changes. And the only thing that's different is one electron. We have taken one single electron away from our sodium, and its properties fundamentally change. The reason why this happens, why the difference of one electron makes such a big difference, is again, if we observe the electron configuration for our sodium, which is neon 3s1, this one valence electron is super reactive. So if the one electron is still present on your species, it's going to be super reactive. If we lose this, and all that remains is a sodium plus with a really nice stable charge, we're going to get something that is not so chemically reactive anymore. And so this is why sodium plus is, not only safe to touch, but safe to ingest. It's safe to interact with in the world around us. We have lost the problematic electron. It's somewhere else now, and all that remains is a product that's very, very stable and safe to interact with. All right, so the magnitude of ionization energy that is needed to remove an electron increases as we go from left to right on the periodic table, and increases bottom up. The wording that is described up on top pertains to the variables that we have observed before, so our quantum number n and our effective nuclear charge Zeph. As we go from top down on the periodic table, we increase in atomic size. We've talked about this before. But it's not just that we increase in atomic size, it's that we increase in the distance between our valence electron out here and our nucleus, which is where all of our positive charges are. The further this distance is, the more difficult it is for the nucleus to hold on to our valence electron. So the further the electron is from the nucleus, the easier it is to lose. So the further this electron is from the nucleus, the more likely it is that we can just put in the amount of energy necessary to scoop it away. Conversely, in the upper right-hand side of the periodic table, where we have not only very small elements in comparison to the left-hand side of the periodic table, but we also have very large effective nuclear charges here. Which means the nucleus, by definition, will hold electrons tightly. It takes a lot of energy comparatively to put in, or takes a lot of energy comparatively that you need to put in to an element like helium in order to kick the electrons off. It is difficult to lose electrons up here. So it's very easy to lose electrons in the lower left-hand corner. The larger the element and the more metallic it is, the easier it is to lose those electrons. Conversely, the smaller your atom is, the more non-metallic it is, the more difficult it's going to be to lose electrons. They're just going to be held too tightly. However, we can lose multiple electrons inside of an ionic species. So what we've talked about so far is just known as the first ionization energy. This is the minimum energy required to move one electron. We're losing the first of all of the electrons that we could possibly lose in some type of electron configuration. So the trend that we just observed, I'm going back a slide, is that it takes more energy from left to right on the periodic table. It takes more energy from bottom up to lose the first of all of our electrons. Now, we would expect the energy that it takes as we go from left to right to be just a constant, steady increase. However, moving forward again, as we can see in the diagram presented here, that is not necessarily the case. So as we go from hydrogen to helium on the periodic table, there is an increase in energy that is required to remove the first electron. And as we also predicted, helium would have the highest of all of the first ionization energies because it's in the upper right-hand corner. We can see here that that is in fact true. As we go to lithium, we can see that there is a pretty large drop in the required ionization energy. That makes sense. We're going down on the periodic table, which means it's easier to lose electrons. So as we go from lithium to neon, we would expect there to be similarly a nice steady increase in required energy. However, we can see that there are two anomalous points. This first anomalous point corresponds to the ionization energy it takes to create boron with a single plus charge. And this other little anomaly corresponds to the amount of energy it takes to move one electron off of oxygen. And before we explain these two anomalies in detail, we can kind of see as we look at other rows presented on the periodic table. So this is row 3 from sodium to argon. This is row 4 from potassium to krypton. Row 5 from rubidium to xenon. We can see that there are some anomalous points that tend to repeat. So here we have some circled anomalous points, here is a circled anomalous point, etc. We can explain each of these anomalies via the electron configurations of the neutral elements. And we're going to apply kind of a similar argument as what we did when creating the ions that correspond to the transition metals. We're going to need the orbital box diagrams to make sense of everything. All right, so let's illustrate the orbital box diagram for boron. So boron has a neutral electron configuration of helium, 2s2, 2p1. So we have one little electron right here in the p subshell. The orbital box diagram for this, we have a 2s subshell right here. It's completely full. And our 3-for-1 deal of all of these 2p electrons, there is one electron still inside of it. So to reiterate, ionization energy corresponds to the energy it takes to lose an electron. If we are comparing beryllium versus boron, beryllium being the element that comes right before boron, it's going to be this dot right here. There's a sudden drop in energy compared to where, or the starting point, this beryllium, if we're observing boron, because we have one sad little lone electron inside of this new subshell. One sad, lonely, little electron. This one sad, lonely little electron exists all by itself. There is nothing it can pair with, nothing else to stabilize it, and the 2p subshell is higher in energy than the 2s. So it's not even that this electron can like go hang out hypothetically with its 2s friends, it's too high in energy. Because we only have one electron present inside of this 2p subshell, it's actually going to end up being easier to lose than expected. So this one sad, lonely little electron is going to be easier to lose than expected when we compare the same situation, the same electron configuration to beryllium, which came right before it. In beryllium, its electron configuration is the same as boron, it just already doesn't even have this one sad, lonely little electron. Beryllium's electron configuration is this. It has a filled subshell, the electrons have pairs, it's going to be very stable in this way. So we increase by 1 electron to boron, this one sad, lonely little electron is going to be so easy to lose. It might as well not even be there. So this explains the anomalous drop in the electron first ionization energy compared to beryllium, because that one sad, lonely little electron, we can just get rid of it, and it's not going to take as much energy as we would expect. All right, oxygen, we can see similarly, there is an anomalous little drop right here. And so we're going to write out the electron configuration of oxygen to make sense of this. And we're just going to jump straight into the orbital box diagram, where this is the 2s orbital, this is the 2p orbital, where we have a total of 1, 2, 3, 4, 5, 6 electrons present inside of our oxygen. Now we can see that there's a little bit of a repeat in terms of pattern. When we were looking at boron, we had one sad, lonely electron. When it comes to oxygen, we can see that we have one cramped electron. There's only one pairing of electrons in this 2p subshell, and the one cramped electron would not mind just getting out of there. So for this reason, it is going to be easier to lose than expected, which is where we can see this little anomalous drop in terms of our first ionization energy trend. We expect, again, the energy just to steadily increase from lithium to neon, and instead we see 2 anomalous drops. The 2 anomalous drops just come from these electrons either being sad and lonely or cramped, and in both cases it's just easier to lose them than one would expect. All of the other anomalous drops that we see following the first ionization trend along the periodic table have similar explanations. We can draw an orbital box diagram, and more than likely what we'll find is that there's one either lonely or cramped electron that's just going to be easier to lose than what we would expect, than what trend would dictate. All right, so far we have explained the ionic radii in terms of trend. We have explained first ionization energy and its trend, again, assuming that in each of these cases we're only losing 1 electron. But again, we can lose multiple electrons. That was how I introduced the definition of the first ionization energy. If we're just losing the first, what happens with those elements where it's actually easier to lose multiple electrons? Things like calcium 2+ or aluminum 3+, which we've already introduced. Well, for observing that trend, we need to discuss successive ionization energies. This is the ionization energy necessary for every successive electron lost, and the nth ionization energy, or I sub n, is equal to the energy needed to remove the nth electron. So in the table down below, what we have written are each of the elements going from sodium to argon across one row of the periodic table. So here we are looking at row number 3 on the periodic table, right again from sodium across the periodic table to argon, top down on this table. And what the rest of these headers symbolize is how much energy it takes to lose 1 electron. So here is our first ionization energy. We lose 1 electron here. Second ionization energy, these are the energies needed to lose 2 electrons, etc. So we're losing 3, 4, 5, 6, and 7 electrons here. Now what's notable about this, first of all, if we move horizontally across the periodic table, only looking at the first ionization energies, similarly what we can see here is a steady increase in the amount of ionization necessary. So we're going from sodium with 400 kilojoules per every mole of energy required all the way to argon with nearly, right, or over 3 times that amount that's required. So we are looking at this steady increase. We are still consistent with our previous periodic trend. Even the expected anomalies are here and here. With successive ionization energies, though, we can also make a pretty good prediction about how many electrons are going to be stably lost before suddenly we start cracking into our like noble gas core. So for instance, sodium, we know that it's going to be very easy to lose 1 electron because it only has 1 valence electron. So the amount of energy necessary to lose that 1 electron, we can see here, it's approximately 500 kilojoules per mole. And suddenly, as we go into the next ionization energy, the amount of energy necessary to lose 2 electrons, we can see that there's this huge inflation of the energy necessary to crack into that new shell. This hyperinflation of the necessary energy, this ionization energy, comes about because if we consider we've lost 1 electron already, the electron configuration of sodium is at this point neon. It is a noble gas core. If we want to lose another electron, we're going to have to crack into, here's my pickaxe, we're going to have to crack into this noble gas core, which is going to cause neon 2+, or not neon, sodium, 2+, to lose the neon configuration and become unstable. Right? We have lost that with which we were striving for. We wanted a noble gas configuration, and now we've lost it. So this is why we see this huge uptick in the amount of necessary energy in order to lose 2 electrons for sodium. And each of the huge upticks I have marked here in like the dark kind of neon grayish, not neon, what's the word I'm looking for? This dark grayish kind of blue color. I don't know where I got the word neon in my brain, probably because I just looked at this. Regardless, magnesium, we would predict, based off of its electron configuration, that it'd be stable losing 2 electrons. So for the first electron that we lose, we see, yes, there is a little bit more of an energy requirement compared to sodium. If we want to lose the second electron, it's going to take approximately twice the amount of energy. That makes sense. We lose 1 electron, it's going to take a certain amount. Lose the second electron, it's going to take twice that amount. But we can see, just like before, when we were discussing the sodium case, magnesium, if we want to lose that third electron, we see this huge uptick in the amount of energy required. In order to lose 3 electrons with magnesium, it is going to also have to crack into the neon shell, the neon noble gas configuration, in order to form. For that reason, magnesium 3+ is also unstable. We have lost too many electrons here. And the same argument can be made for aluminum 4+. We've already looked at the electron configuration of aluminum, right? That was one of the main block elemental examples. It's stable losing 3 electrons outside of the core, but to lose a 4th, we see there's this huge uptick in energy needed because, again, we're cracking into the noble gas core. We are creating an unstable ion. And that's true as we go all the way down the periodic table. We expect elements like chlorine, which, yes, granted, is more stable gaining electrons, but bear with me, it does have 7 valence electrons. So we can see there's this steady increase in the amount of energy necessary to lose each of these electrons. And then there is a, outside off of this graph, a larger uptick that we would predict. Sulfur, which is probably a better example why I didn't pick this one in the first place. Sulfur, we can see has 1, 2, 3, 4, 5, 6 pretty low-lying, linearly increasing ionization energies, and this 7th is just too big. The 7th ionization energy requires too much. And so to lose this 7th electron, to reiterate, means that we're going to crack into this noble gas core, which makes an unstable ion. All right, so successive ionization energies. If we know what the reported successive ionization energies are for a certain elemental species, we can also backtrack and predict what column of the periodic table it corresponds to. So I'm going to clear this off a little bit. Let's say that you are told that the ionization energy, or successive ionization energies for a particular element, let's see, I1 through 3 are low, and the fourth ionization energy spikes. Well, if there's a spike in the fourth ionization energy, that means it was relatively easy, I'm going to put that in quotes, to lose 3 electrons, which means the element is probably a group 3 element, something like aluminum, right? The first 3 were easy, the fourth one is hard. This means that you're going to be working with an element that can easily lose 3 electrons, and the fourth one is going to become increasingly difficult because you're cracking into its noble gas core. All right, well, I did give the strange forethought as I started, I think, speedily rambling, which I apologize for. When I was discussing sulfur and chlorine, right, we can explain where the steady uptick of their ionization energies are if we are losing electrons, but these are elements that do prefer to gain electrons. So how do we rationalize them losing electrons when they'd prefer to gain electrons? Well, first and foremost, if you put enough energy into something, you can always take its electrons away. You just have to give it enough energy. But if we did want to cooperate with the elements like sulfur and chlorine, which do prefer to gain electrons, how do we define the gaining of electrons as opposed to ionization energy, which by definition corresponds to the loss of electrons? Well, this corresponds to what we call the electron affinity. This is the amount of energy that is released when an atom in the gas phase accepts an electron. So electron affinity creates anions, whereas the ionization energy that you put in creates cations. So one corresponds to creating a positive ion, the other corresponds to creating a negative ion. Now this is a chemical property, just like the ionization energy, where the identity of the atom is going to chemically change. A really great example of this is the counterpart to sodium, which is chlorine. If we take chlorine gas in its natural form, this is a radical species. Similar to the sodium, it is going to be very reactive. I mean, it's so close to its noble gas configuration. It just wants one more electron. And as a result, it's going to be incredibly reactive in its pure elemental state. Well, if we compromise with it, if we go along with it, if we do give this chlorine its one missing valence electron, what we end up with is chloride, which is different than chlorine. Whereas chlorine is incredibly reactive as a species, chloride goes along with sodium chloride, right? As a generic example, this is table salt again. Sodium and chloride work together to create a delicious flavoring, right? It emphasizes the flavors of foods. If you were to consume it, it's really stable to ingest. In fact, like your cells, cells inside of your body help to maintain ionic charge based off of like chloride gradients inside of your body. So chloride is actually a really beneficial thing to have inside of you. Chlorine, not so much. And the only difference again is one electron. If you give chlorine its one electron, it has a really stable electron configuration. And that stable electron configuration means it's not going to be super chemically reactive. All right, so now that we've talked about ionization energy, not only the first, but also the successive, we could have a similar conversation with electron affinity. For every successive electron we want to add, we would expect to see similar trends based off of the orbital box diagrams. So instead of going through all of that for electron affinity, let's just work through an example problem pertaining to ionization energy, because the same types of arguments can be applied. So which of the following elements would you expect to have the lowest first ionization energy? Now, without going back, right, no cheating, which of these elements in the third row of the periodic table would you expect to have the lowest first ionization energy? Similarly, which element would you expect to have the highest third ionization energy? And if you've paused and answered the question, the lowest first ionization energy corresponds to the element that can easily lose one electron. This will be an element that just has one single valence electron, and if we observe the list, ding, 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 sodium is going to be the winner. Now we can go back to the successive ionization energy table to confirm this, which we'll do in a moment. Let's turn our attention to the other question though. Which of the elements in our list is going to have the highest third ionization energy? Well, another way to think about this, if the third ionization energy is the highest, what this means is that it was easy, and again, I'm putting this in quotes because we do have to put some energy in, it means it's easy to lose 2 electrons. So in order for an element to easily lose 2 electrons, it's going to have 2 valence electrons. The element that is on the list of having 2 valence electrons is magnesium. All right, so let's take this information and go back to the previous table. And we'll clean it up a little bit. The element that has the lowest first ionization energy, so we're looking at this column, we can see is right here, right? It is sodium. This is exactly what we predicted. And if we turn our attention to the third ionization energy column, we predicted that magnesium would have the highest third ionization energy. And in fact, if we look across the entire column, even though yes, the ionization energy does increase from aluminum to argon, it is magnesium that has the highest third ionization energy because we have to crack into that noble gas core. All right, so whether we are observing first ionization energies, successive ionization energies, or again, electron affinities, we can make similar arguments about whether or not we would expect it to be easy to gain or lose certain numbers of electrons completely based off of electron configurations. And with that, we are done for the day. So we have now talked about all of the periodic trends that we need to talk about, whether it be the size of your atom or the likelihood of it turning into a particular ion. We can predict electron configurations for certain elements as well as their ions. We can predict certain sizes, whether it be for a neutral element or a corresponding atom. We can predict, conductivity. We can predict electron affinity. We can predict all of these things, all of which have to do with the electron configuration of your atomic species. All right, so as we move into chapter 5, we're going to look at the implications of some of these chemical properties that we've introduced here, most notably ionization energy and the most stable ions that arise based off of electron configurations. We are going to finally turn our attention to molecules. Smiley face. Right, we started with the small and we are making our way slowly to the big. Since there is nothing else, though, to discuss here, I'm just going to say, hey, if you have homework, do your homework, and until next time, class is dismissed.